Thanks very much, Ruben. Okay, so, and thanks, Steve, once again for having me. All right, so for those who were here last week, and I'm sure lots of you were, that's where we left it last week. And you might have heard Steve in the beginning there. So it is, it's quite in depth, and I know that I'm brushing over it. And really, what we need to do when you do it properly is to take a little exercise, do it yourself, do one or two examples and work. Because, you know, I've found in anything, the only time you really understand something is when you've done it yourself. And this is a hell of a lot to take in. So let's go from where we left it. The last thing we did is we worked out the exact size with total flow at an exact velocity and accommodate an exact friction loss. Okay, and what we ended off by saying is that the result was completely mathematically correct, but as plumbers, and we would know, it would be totally impractical to do things like that. And so why didn't we just add up all the flow every time we do a pipe size? So now what we go to, and that example, just to remind you, was to clearly understand the relationship between velocity and flow and how that ends up back in a pipe size. Okay, now what we get to do is to start really designing. And okay, I made the point about SI units. I think I've hammered that home enough times. So we think in liters per minute as plumbers, but when we do formulas and stuff, we've got to keep going back to those SI units, or else we get the wrong thing. And so I remind you of that as well all the time. Okay, but what we really wanted to get to was that when we do pipe sizing for an actual project, like a school or a stadium or a house or anything, there might be, for example, 300 toilets in a hotel. They are never all going to be used at the same time. So how on earth do we know how many will be used? And when that many are used, how big the pipe must be? And so that that's called probable demand. So that's like, you know, to simplify it, if there's 5 toilets in a house, probably 2 might be used at the same time. So let's make sure there's enough water for both of those out of the 5 to flush at the same time. If there were 5 toilets in a school and the brake bell went, there's a very good chance 4 or 5 of them would be used at the same time because everybody's been waiting and they rush, and you know, so the probability of simultaneous use is what we base the demand on. And there are a number of different ways to get to that. None of them are pure science. They're all empirical, which means it's like a hypothesis. It's based on some research. It's based on some theories. They might have logged some data over time, as in the FLUSHMASTER tables. And that goes back to your source of establishing the probable demand. So this is not as pure and accurate as the previous exercise we did, but it's much more practical in plumbing terms. And most certainly when you use them, you'll get a design that works. Okay, so as I've said there earlier, when you've got different types of buildings, different types of plumbing situations, you've obviously got different demands. So for a massive big thing, you're going to end up with massive big pipes. And for a teeny little, you know, 1 bathroom flat, you're obviously going to have a teeny little 1/2-inch pipe. So let's go to the methods of establishing probable demand. I hope everybody understands what it is now. So there are, the one that we're looking at here is called a load unit system. So it says that if you've got a 1/2-inch tap, I hope you can see the mouse, it's going to flow at about 8 liters a minute. We know it might go to 12 liters a minute. Okay, and they give it a rating. Okay, in this system, I can't tell you the name of who designed it, but they give it a rating of 0.3 load units. Okay, and if it was a 3/4 tap, it would have 1 load unit, and so you go. So this rating is not a rate of flow, it's just a unit. It's like a number. And to get to the total flow, what they do is they'll count up how many of each fitting, you've got in the design, add them all together, times it by a quarter, and then they take the square root of all of those, okay? And they times it by 0.25. So one load unit, by definition, I had to do it in my masters. One load unit, by definition, would be quarter of 0.25 liters per second, okay? And she times it by 60 to get it back to liters per minute. So that's one set of load units. SANS 10252 have got their own values. It amounts to the same thing. They add the flow rate instead of the units, and they would then take a decimal exponent, which is the same as taking the square root over 7. Okay, so let's take an example, and don't worry if you don't get it right now. One day when we do the examples, we're going, and I'll show you later how you do the actual thing. But the point is that for each half-inch tap, it's worth 0.3 load units. For each FLUSHMASTER's flash valve, okay, they don't use it on that system because it's too big. But for each system, you'd have 0.3 units, or for every bath, you'd have 4 units. Okay, so let's, okay, then on the FLUSHMASTERs, we've got these probability tables. There's a whole file full of them, and they would take for each different type of building. So for an office building, for that many flush valves, you'd need that rate of flow on a one pipe system. And built into that rate of flow, it's also saying, well, if there's one toilet, there's also going to be a basin, there's probably also a kitchen mixer and whatever else might be in the house. And on a junior FLUSHMASTER, it would be that 73 liters a minute. And you can see as the number of valves increases, it doesn't go 73 times 2. It goes up by a little bit, and a little bit, and a little bit. So these flow rates were based on research. Again, remember I said it's empirical. So it's tried and tested. These were actually done by Sloan Valve all the years ago in America. So they had data loggers in hundreds of different buildings, and they gathered all this information and they tabulated it. Okay, so when we were doing FLUSHMASTERs, we definitely referred to these specific tables. You can use load units, but it doesn't work well because you end up with hectic sizes, because they've got to, for one, they've got to make a really big load unit, and when you add them all up, you get to ridiculous sizes. So this is the better method for FLUSHMASTERs, with a little job here for some junior FLUSHMASTERs. We say it's a hostel, okay? And we're going to use the tables that look at hostels or residences and that kind of a job. So we can see here that our mains pressure is 680 kPa, and we can see all the lengths and the heights and the number of valves. So we start off, we did say it earlier, remember that it's got a 3/4 inlet. It needs 150 kPa flow pressure to work. It's got a peak flow of 65 liters a minute. Okay, and for urinal valve, you only need 30 kPa, but we're not going to do urinal valves now. So these are all toilet valves. So we start off with this primary information, as we did with the last one. So the first thing we know is it's a hostel, right? Because the architect told us it's a hostel. Our mains pressure is 680 kPa. The loss of head is going to be to the highest point in the system. So we go up 6 meters. So we're going to lose 60 kPa. The required pressure is 150. Why? Because we've just said a junior FLUSHMASTER needs 150 to work. Okay. And then the distance to the critical point will be from the start. You can see we're adding up the segments. Okay. So it's 29 meters to the critical point. Okay. And now we've got all those parameters in there. And to get our permissible loss per meter, okay, how many kPa? We start off with 680. We definitely need 210 because we've got to accommodate that loss of head, and we need 150 at the valve. So we can afford to lose 470 kPa of dynamic pressure. And if we share that out amongst all 29 meters of the system, it tells us how many kPa per meter we can lose. Okay, so we can lose 470 divided by 29, which means we can afford to lose 16.2 kPa per meter. Now we go to the segments. We had to first label them all, just as I showed you in the last time. Every time there's a change, give it a new label, A, B, C, D, and we put that on a table like this. Okay. Once you've made that table, you would count per segment what the length is. Segment A, we can see, is 7 meters long. It's those 4 plus those 3, and it's feeding all of these FLUSHMASTERs. So it's feeding 12 FLUSHMASTERs. Okay, and so you do the same thing for each and every segment all the way down. The segment B is not feeding all of them. It's finished with that one. So now it's only feeding 11, and so you go. On segment G is only feeding those 5. Okay, so it's quite detailed and specific, but you tell this table exactly what's feeding what. Now we go back to these tables that I showed you. We see, remember, I showed you that FLUSHMASTER table. So they're junior FLUSHMASTERs. So we see we've got 12 FLUSHMASTERs. There's between 11 to 19. We need 136 liters per minute of probable flow. So we take that value of 136 back to our little schedule. Okay, once again, do the same thing for each and every segment. Okay, so there's all our required flows per segment. Okay, and we're now going to go and look at these friction loss tables. So remember that we said we need 136 liters per minute, step 1. So we go down the side here, and we find 136 liters. That's not enough. That's more than enough. So that's the one to use. Okay. We could afford to lose 16.2 k per meter. So let's just quickly check. There we're going to lose 13.9. It's less than 16. So we're good to go. So as far as friction goes, 28 mil pipe will do it. But we've got a second criteria to fill. And remember, we don't want that water to go faster than 2.5 meters per second. So let's check that now. Okay, so friction's good. Now we're going to check, friction's good. Now we're going to check velocity. Okay, so we go on the bottom here at 2.5 meters per second. This is how much water each of those pipe sizes can deliver. So at 2.5 meters per second, a 28 mil pipe can give you 74 liters per minute. How much do we need? We need 136. So is that enough? No, it's not enough. So we have to go and find where we get enough water to feed that 136. And if we don't, what will happen? The water will go faster than 2.5 meters per second, which we've said we don't want. Okay, so we go and have a look here. That's still not enough. That size is enough. And so we run up to a 42 mil pipe. And when we had a 42 mil pipe, we've now accommodated both the friction and the velocity. Okay, so now we're going to take the same exercise and do it for every segment and put that information back onto your schedule. Okay, and that will give you your pipe size. So again, you can see they're big pipes, and we're going to talk about that later, because you and me as plumbers know that if that one was 22 mil, it's going to work. But what's going to happen? It's going to go faster. It's going to be a bit noisier. But we've got enough pressure. We've got enough friction error. It's not critical. You can make a call on it. Okay. But that would be, if you did this job for an architect, you want to be 100% sure it's not going to go faster than 2.5, and it's definitely going to accommodate those probable flow. This is a safe way to go. And if somebody does it and you quote for it, well, that's nice. It's a nice big job with big pipes. Okay, so that was a junior FLUSHMASTER. Let's go now and do a load unit system. Okay. So let's check how I'm going for time. All right, so this is now not using FLUSHMASTERs. This is just a typical little small jobby you would do. It could be a house, or it could be, in this case, a little clinic. So there's a fair bit of plumbing, be a nice job to get, but it's not a big, massive commercial thing. So we're going to use these load unit tables. Okay, load units, again, I talk about the SI units. Load units end up in liters per minute. So the answers we bring back are loads. They've already done a calculation on the formula before, so we don't have to now be in SI units. So if you think I'm contradicting myself, I'm sorry. But okay, so let's take that job. We do the same thing. We know from the spec that all the toilets are going to just get cisterns. They're not going to use FLUSHMASTERs. The basins have got electronic taps, but it's a little half-inch inlet tap. We've got medical mixers in the sink. Okay, and in the kitchen area, they've got a normal star sink mixer in there. So there's nothing particularly high demand. They're all conventional plumbing size fittings. So do the exact same thing. We size up the layout where we're going to put the piping. So let's say here we're running it in the ceiling and we're going to drop down. It's diagrammatic on the drawing anyway. So in real life, doing the plumbing, you're going to find the right place for it. But to get to the size, we're going to lay it out on the plan like that. And just a little rule of thumb. So I'm not going to do a whole system for hot and a whole system for cold. Whatever you do for the cold, you just echo that for the hot. And unless, of course, the hot comes from a completely different circulated system or something, which we're not going to go into today. So we're only going to work out one of which is for the hot and just apply the exact same to the cold pipe. Okay, so precisely the same thing. We draw up the table, change each segment's name. A, okay, it's feeding everything. B is only feeding those things. C, so you label each change in the segment, and we bring it onto this table over here. So A is 5 meters long. It's feeding all of these things. So you can see I've got 1 sink, 8 basins, 3 WCs. If I add up all these load units, 1 times 0.6, 8 times 0.4, 3, I end up with 4.7 load units. Okay, and I said, I'll show you how you do it. So if we took those 4.7 load units, the flow, Q means flow, Q is equal to 0.25 times the square root of 4.7. So the square root of 4.7 is 2.1. Square root of 4 is 2. Okay, 2.16 is the square root of 4.7 times 0.25 gives you 0.54 liters per second. It tells you there the answer is liters per second. We want to get back to liters per minute times 60. So for this job, we need 32.5, let's call it 33 liters per minute. Okay. Do the same thing all the way down. I've just moved the table. So for each and every segment, you end up with a required flow. Now we do precisely the same thing, except this time I'm going to go to our SABS tables, which I think I did show in a previous talk quickly how to use them. So this is, if those of you who've got the 0252 document, you will recognize this hell of a squiggly. So let's start. On segment A, we need 33 liters per minute. So you come down to the x-axis here. It tells you this is the flow. Okay, you go and find 33 liters per minute. Okay, remember that we said we're going to work at a velocity of 2.5 meters per second. So we're going to find this 2.5 meter per second curve. It looks like a straight line. Again, it's a curve because if all these little lines were in a nice blocks, then this would be a curve. Okay, so that's the 2.5 meter velocity curve. That's the one we're going to reference. Okay, now we take a line straight up till we cross that. Okay, and at that point, we would see which is the closest pipe size. Where the pipe size is, here's all the pipe sizes. We look for the pipe size, not less than, closest to, that crosses that one. Okay, so there it is. Okay. and that pipe size is a 22 mil pipe. Okay, the next, so we take that 22, take it back to the schedule as I've done there. Now we just want to make sure that we've accommodated the permissible friction loss. We're allowed to lose 16 kPa per meter. So now we go here on the y-axis, and you can see hydraulic gradient. So they're confusing you. I call it friction loss and I work in kPa per meter. They call it hydraulic gradient, and they talk in meters per meter, just to confuse us. So a meter per meter, how many kPa is 1 meter of head? It's 10. Okay, so we're allowed to lose 16. If we go across from that point, we're going to lose 0.4 meters per meter, or if you want to think in kPa, we're going to lose 4 kPa per meter. Okay, it's much less than we're allowed, so we're good to go. Okay, so we've now matched both the friction and the velocity requirements. Okay, so you do the exact same thing for each and every segment, and after all that hectic science, you're going to end up, and it says you start off with a 22 mil pipe, and as you branch off to the little areas, you're mostly ending up with 15 mil. Okay, and does that seem like real plumbing? Totally. It seems to be exactly what we would do. And so that is the load unit system. And okay, time's charging along. I've got 6 minutes to do the last example I'll show, which is a tank feed system to standard FLUSHMASTERs. So same thing again. So here we've got our tank and 3 stories with standard FLUSHMASTERs. The exact same thing. Lay it out, draw up the segments. So every time there's a change, give it a new name. A, B, C, D. So you go. We need to know the length and we need to know the height. And our source of pressure is going to be the height now because it's depending on gravity. So it'd be 4 meters times 10 times 9.81 if you want to be exact, would give us an available pressure of 40 kPa at the worst point. Okay, highest point, which is going to have in this case the lowest pressure. If that one works, so it won't be this one, because in this case the pressure there is only going to be 40, and in here it's going to be much better. So if this one works, we know for sure those ones will work. Okay, so remember that a standard FLUSHMASTER needs only 30 kPa, but it's got a peak flow of 105 liters per minute, which means it needs volume. So that's why it's got that almighty big 1.25 inch inlet. Okay, so this information on the primary criteria table we're going to get. We know the height of the tank, we know how much that needs, and we know the distance to the critical point. Okay, that's the length for friction. We take the longest point. The pressure, we take the highest point. Okay, so there's our values. The tank height is 4 meters, which will give you a static pressure of 40 kPa. This mouse disappears from time to time. Okay, and then we need 30, so we can only afford to lose 10. Once again, we design it to 2.5 meters per second, and we've got a distance of 19 meters to the critical point. So we can only afford to lose half a kPa per meter. Okay, draw up the table of the number of valves. Okay, go and get this information as I showed you with the juniors. Go and get it off that table. So with 1 valve, you need 105, 2, you need 182, and so you go down. Okay. So we take our schedule that we've drawn up. There's all the lengths. 15 FLUSHMASTERs in segment A falls in this category. We need 318 liters per minute. So you take your 318 liters per minute back to the table. Do the same for all of them. Okay. So every segment's got a required probable flow. And then in this case, we're using just simple friction loss tables. So at 318 liters per minute, there it is. Okay, we're allowed to lose how many? 0.52 kPa per minute. Okay, so there is where that's the band which is gonna give us that friction loss, and down at the bottom, or less than that friction loss. Okay, At that rate, we're going to lose, it's actually a little bit more, but we're not going to go to a 3-inch pipe. And then we're going to check at that velocity, we can deliver 500 liters per minute. We only need 300, so we're safely covered. Okay, do the same thing for each and every segment. And when you come back to the drawing, you're now going to go and, so our outlet there is going to be a 67 pipe, okay? And on the branches, we're ending up with 54. And obviously, as we tee off to the standard FLUSHMASTER, we're going to go down to 3/4. There are, just for interest's sake, there is software which will do it, analyze it much better, and you'll actually end up with more efficient sizing because it can look at the change per segment. Okay, and then, okay, what are really for our own guys? So when you go on to do designs, remember to stipulate specific things like your, detail. If there's a pumping system or a solar or a geyser, you put it on the drawing as well. Okay, so really what we've covered, and as you said right in the beginning there, it's a thing we need to work through practical examples, but what we've covered is to get some of the understanding of the fundamentals, a little bit about pipes, and we've given an example of using total flow, okay, designing for junior FLUSHMASTERs, using the SABS tables, a typical gravity fed system. There are software options, okay, and what we said there is just to include any specific details. And generally, the last note I make is that large piping and a reticulation design, it's expensive, it's a safe design, and it's quiet, whereas smaller diameter is cost efficient, it can be noisy, and it could cause starvation if undersized. So remember that as a lot of this is empirical. 2.5 meters per second ends up with very big pipes, as you saw there. So if we push it a little bit, the pipe sizing will come down dramatically. It won't not work, it's just going to get noisier. There's a threshold where things won't work. So for example, if you took a 1/2-inch pipe to a junior FLUSHMASTER, it won't work because you can't get that 65 liters a minute. But if you took a 3/4 pipe, and you should have had 28 to get your 2, it'll work. It's just going to be noisier. Steve, IOP guys, thank you very much for having me. And all the guys, thanks a lot.